gentlemen, and welcome to another segment of Astronomy Toronto. My name is Randy Attwood, and I'm a member of the Toronto Centre of the Royal Astronomical Society of Canada. Astronomy Toronto is Toronto's astronomical news magazine, which is seen here on Rogers Television every month, usually the first Wednesday of the month at 8 o'clock. We usually look at topics of astronomical topics, galaxies, what's going on in Toronto, what professional and amateur astronomers are doing here in the city of Toronto. But we're going to digress just a bit this time because I'm very happy and very honored to welcome to Astronomy Toronto Dr. Art Hunter, who is the project manager for the RMS, or the Remote Manipulator System. Many of you know as the ARM on the shuttle Columbia. So Dr. Hunter, thanks very much for coming by today.
It's very nice to be here.
I think a lot of people are excited about the ARM. I think everyone knows about it, but I think what we're going to do tonight is maybe take a deep look at it and talk about the background of Canadian astronomy, Canadian space research. I think it's had a very, very long history.
Indeed it has. The amount of money that Canada has invested and the number of people that have been involved, we have quite an impressive record of involvement in space and have had very impressive results. The first real interest in space was way back, I would say, in the First and Second World War time frame, where people were interested in the ionosphere, obviously because of the implications that had on our communications. And at that time, in the early days, it was the University of Saskatchewan and the National Research Council, along with the Defense Research Board, who spent a lot of effort trying to work out some ground-based techniques of probing into space. Of course, these came under a number of headings. The optical observations were obviously the first, which you folks use quite regularly, including many universities, including the Hertzberg Institute of Astrophysics, which is part of NRC, the Canadian Armament Research Development Centre, known as CARDI, as well as University of Laval, Western Ontario, York University, University of Montreal, University of Saskatchewan, as well as the Canadian Atmospheric Environmental Service. Then we moved from there on into radio observations using ionosounds, and primarily during World War II, the Defense Research Telecommunications Establishment was the primary agency responsible for that.
What is that? Is that bouncing radio off the ionosphere and seeing what happens to it?
Yes, indeed. And there's still stations in Canada which are doing that type of research. Then in the late 40s, the University of Saskatchewan and University of Western Ontario became involved in these observations as well. Magnetic observations, which were looking at the ionosphere as well as the magnetosphere, were being done by Energy, Mines and Resources, Department of the Canadian Government, as well as the University of Alberta and University of British Columbia. Then we progressed into looking at cosmic rays, primarily through the facilities of the National Research Council and the University of Calgary. And as time went on, we started looking and trying to get our instruments off the ground and up into the near space, as the high upper atmosphere as we can go, and the first technique used was balloons.
Well, this allows you to see a lot more if you get above the atmosphere, isn't it?
Well, balloons can only go so far into the atmosphere, but one is interested in the phenomena at that stage as to what is happening in the upper atmosphere because of the implications to us on the ground concerning communications and the phenomena that we all experience in the communications business with noise and the skip that all our radio amateurs are aware of, and the CBers are certainly used to talking skip. In any event, that's all due to the ionosphere. The University of Saskatchewan and the University of British Columbia, as well as the University of Montreal, were all involved in the early launches, whereby the instruments left the ground and were taken to the upper atmosphere to make the necessary measurements. Then by the time we got to the 50s, the instruments going aboard balloons started looking at cosmic rays as well as X-rays and trying to understand what these phenomena were all about. Universities of Calgary and Saskatchewan were also quite involved in that. The launches of the balloons were from 3 locations, from Cold Lake, Alberta, from Yorkton, Saskatchewan, and Churchill, Manitoba. Rockets started in the 50s as well from our friends at the Canadian Armament Research Development Center and Bristol Aerospace, who developed the Black Brant family of rockets. And these were launched out of Churchill, Manitoba.
So would these rockets just be above the atmosphere for a few minutes and do all the work that can only be done above the atmosphere?
Oh, yes. There's quite a family of them, in fact. Not many Canadians are aware that we do have a rocket launching facility in Churchill, Manitoba, and that we do build them right here in Canada. The United States has, in fact, purchased and used a number of the Canadian-built rockets, primarily looking into the Aurora, because we geographically have a unique position to be able to probe the Aurora. But from there, another interesting development occurred in the 1960s, early 60s, and that was a gun-launched probe, whereby 2 large naval guns were welded together, providing a 16-inch diameter gun barrel that was 119 feet long. This was located down in Barbados and provided the opportunity to very accurately place your scientific measuring instruments in the same location. The gun itself had a number of advantages, one, of course, being that you could reload it and fire it into the upper atmosphere every hour, so you could watch a transient phenomena with a number of launches. One of the most unfortunate aspects of it was that your payload had to be designed to withstand 25,000 Gs, or 25,000 times the pull of gravity.
Putting your payload in a bullet.
Indeed, that's exactly what it was. That facility has since been retired, where we moved on into satellites. The first Sputnik, launched by the Russians in October 1957, and of course this launched us into the space era. Canada became very interested in using satellites to probe the upper atmosphere, to augment all the work that had been or had been collected in the past, all the information. And we selected at that stage what we called the Topside Sounder program, where we were going to explore the ionosphere above the area where there was maximum ionization, and in this way to try and understand the phenomena much better than we had by looking up from the bottom. And again, the prime motivator for looking at this was to understand the phenomena that was happening with our communications. Canada being geographically a very widespread, large country, very lightly populated, particularly in the north, that communications is really one of the very important phenomena that we must address if we are going to open up, particularly the Arctic, and of course maintain communications in a east-west country, bearing in mind most of our population lives within 200 miles of the 49th parallel. This Topside Sounder program resulted in the building of what we called the Alouette-1 spacecraft. That was launched in September 1962, and this marked the fact that Canada was the 3rd nation in the world to launch its own satellite. There was another Alouette that was launched as part of the program, as well as 2 other spacecraft, which were called ISIS, which stands for International Satellites for Ionospheric Studies. And in fact, it was an international program. There was 7-odd countries that participated in it. As a matter of fact, one of the countries involved in the ISIS program was the UK, and we were using a ground station located in the Falkland Islands, which is a topic these days.
Sure is.
Then we moved into satellite communications and became involved in the international consortium known as Intelsat, and our Canadian participant in that is a company called Teleglobe. And they have Earth stations at Mill Village in Nova Scotia for transatlantic communications and at Lake Cowichan, BC for trans-Pacific communications. In September 1969, Telesat Canada was brought into being, and as a matter of interest, I joined Telesat Canada in April of 1970, and we launched the first of the Annex series in November 72. Annex 2 and 3 were launched in April 73 and May 75. Both or all three of these satellites were operating in the 4 to 6 gigahertz region and are primarily designated for communications.
So these are all in an orbit, which is called a geosynchronous orbit, which
Right.
I guess they're so far up that they go around the Earth once a day, so they're always over Canada?
That's right. They're rotating around the Earth at the same rate that the Earth is rotating, so for the observer on the ground, they are stationary. Each one of these satellites carries 12 channels for communications. Each channel can carry either one channel of color television or 960 voice communications channels. In December 78, the Anik 4 was launched, and that works in the 12-14 gigahertz region, again for communications. And in November 1982, the next of the Anik series is expected to be launched on the Space Shuttle flight number 5. And there is even another generation, what is known as the Anik D series, which is also due to be launched in the very near future. After the initial launches of Telesat, we began to explore other ways of communicating, bearing in mind that the Telesat vehicles, the early ones, were spin stabilized, in that they were spinning vehicles with an antenna that was despun, so it was stationary as the rest of the vehicle rotated underneath. There was a program started by the Communications Research Center out of Shirley Bay, just outside of Ottawa, and this is called the Hermes satellite once it was launched. This was a joint program between the Department of Communications, NASA, and the European Space Agency. It worked on the 12 to 14 gigahertz range, and it was launched in November of 1974. We've been involved through our friends at the Energy Mines and Resources and the Canadian Centre for Remote Sensing, looking at, through cooperative arrangements with NASA and other U.S. agencies, using their satellites to look back at the Earth, remote sensing, as well as for weather observations. So we've participated in international programs of this nature and have made use of the data which those satellites make available to us.
How did the contract for the arm for the shuttle come about?
Well, just let me get there. We're slowly getting there. CSAT was another one that we participated in. And of course, we're interested in the seas, again, because Canada has the longest coastline of any nation in the world, and so we're very interested in knowing what's going on in the seas. However, that one failed about 2 months after launch, which was in May 78, but we're still exploring other ways that we can try and find further knowledge of what's happening in the sea by using space. We also have search and rescue payloads, which are going to be launched in late 82 aboard weather satellites, and this will greatly enhance our capability to get to the crash site of, say, an aircraft or a ship in distress.
Are these geosynchronous also?
No, these will be low Earth orbit satellite or orbits which are normally used by weather satellites. And then we come to the remote manipulator system, which in the late 1960s and early 70s we were in discussions with NASA whereby they were willing to, or they were looking for international partners. They were saying, won't you come and participate in the development of this next great adventure of man in space. We at that stage looked at what our capabilities were, and we worked very closely with industry, primarily Spar Aerospace here in Toronto, and determined that we had a capability to build mechanisms as had been shown in the involvement in the previous space programs, because Spar indeed were involved in the early Telsat builds, as well as communications technology, satellite. They were quite heavily involved in that. And they had been involved in previous NASA programs for the Apollo series and what have you. So these were primarily, their involvement was primarily in space mechanisms. We took a look at the orbiter and said, what is it that we can possibly build? What do we have a capability at? And the remote manipulator system seemed to be a natural in that it was a mechanism and it could be readily separated, as it were, from the rest of the orbiter. It was not an integral part. It's not like building a main engine. You can you can take the arm away separately and develop it on its own. And we looked at our resources and said, fine, we think that we can afford to do this. And after many discussions with industry and amongst government officials, we finally signed a memorandum of understanding with NASA. The National Research Council signed on behalf of Canada and NASA on behalf of the United States to undertake to develop the remote manipulator system.
Well, I guess a lot of people had to work on this. The main construction and action was up at Spar in Weston. I think we have a film of this. Maybe we could roll that tape and we could talk over it as we see the step-by-step. I guess it's the construction and the layout of the actual arm, isn't it? It's not a test model that we'll be seeing, but it's an
No,
actual...
this is the footage that you have is during the design and build of the Space Shuttle arm. Now, here is the simulator facility at Spar Aerospace, and that was Murray Morgan from the National Research Council, one of our test pilots, who was very instrumental in helping us out with the early problems in the design. Here you can see the computer is responding to his inputs, and a math model of the arm is going through the paces under every command. You can see him using the hand controllers there and watching what happens. Now, this is a clear indication that part of the control system passes through the man. Of this space robot, the control is affected totally by man. Whatever he tells it to do, it responds accordingly.
It's also in real time. It's a fascinating thing to try. It's just like playing a video game, really, but it acts immediately on what you do, and it's as if you're in space.
Well, here's a simulation of going up to try and pick up a payload, and you can see a target there that the end effector zeroes in on. And this is what it's not actually what the operator sees, but it's certainly a good simulation of what. Now here is some footage of the build of the arm. This particular piece of equipment is the end effector. It's a grappling mechanism, and you can see here as the fellows rotate the mechanism by hand, how the 3 snare rings close in around the grapple fixture. And here's a grapple fixture coming into view. Normally this process takes place in 1 second. By the time the operator pushes the command or squeezes the command trigger, those snares wrap right around the grapple fixture and then ultimately causes a rigid interface between the end of the arm and the payload. Now here's the clean room facility at Spar that was used to build up the arm and to ultimately do some testing on it. There's on the arm itself, there's 3 joints. There's the shoulder, which you're seeing here now, and there is an elbow and a wrist, very much like the human arm, with hollow arm booms in between the joints, very much like your human arm. The end of the whole arm is not quite like the human hand, but it is a grasping mechanism, as you saw from the earlier footage. Here's one of the arm booms being brought into place.
What is that made of, Dr. Hunter?
That's made out of a carbon composite material, which is very stiff, but yet extremely light. Each one of those section weighs about 50 pounds and is about 25 feet long. So part of the requirement on us was to be able to build a manipulator arm that was 50 feet long and weighed about 900 pounds. So we had to find and use the most sophisticated materials that were available in industry, and to end up with something that would certainly be as stiff as was desired.
It's interesting too that the space is so harsh. You've got the vacuum of space to worry about, plus you've got the heat of the sun and the cold when you're in the shadow, plus the radiation from the sun. Our atmosphere blocks out a lot of that deadly radiation, which the arm has to be able to withstand.
Yes, well, the materials were selected to be able to withstand the vacuum, and as well as the radiation environment. And of course, we tested all of the components in a thermal vacuum facility to prove to ourselves that they would work once they were on orbit. It was a very extensive program to do just that. Here you can see some of the spar engineers just getting the final alignment of the arm booms being joined up onto one of the joints.
Certainly, too, it had to be reliable. There can't be any mistakes once you're up there. Nothing better go wrong.
Yes, we did have a requirement. NASA was very concerned, as were we, about the safety of operation once we're on orbit. We had to have a fail-safe design, and by that we mean that any single failure could not cause any damage to the orbiter or endanger the lives of the crew. So there are a number of modes of operation, and there's some built-in safety features that prevent the joints from misbehaving or doing what they're not supposed to do. Here's some footage of the NRC project office and some of the people involved during the many meetings and telecons which we had. The whole process of building something of this magnitude and spending $100 million requires a lot of paperwork to flow. As time goes on and the hardware develops further, we get into the test phase, and that produces another mountain of paperwork, all of which is very essential if one is building such a highly reliable system, and to meet a whole host of very stringent requirements.
Well, it's obviously shaped for the arm, like an arm, for a certain reason. Is that just because through the controls, the astronaut could feel that it was his arm that was doing the controlling?
No, in fact, what the astronaut does, he literally flies it. He envisages that he sits on the end of the arm, out in the end effector, and when he says go left with his hand controller, he thinks that he's sitting on it. You can imagine the configuration. You can get it in where the end effector is looking at you straight in the eye, and you say go left. Well, it's really right to you, and you can get all confused that way. And if you happen to rotate the arm, up is down, and all that. So you have to vision yourself sitting there. Now here's a camera that is being installed at the elbow location. There is two cameras on the arm. One is at the elbow, which has a pan and tilt capability, and you can see the fellows putting that into place. And there is another one at the wrist, which is very useful device in terms of being able to get up and rendezvous and grapple a payload, either a free flyer or one that's in the cargo bay.
So during the operation, you can look at it live through the windows or look at the TV views.
Right. Now here's astronaut John Fabian going into the simulator at the SPAR facility, and he will be flying on Flight 7, which will be the mission which is going to be the first capture of a free flyer and the first time the arm is used to release a payload and to also rendezvous with it and capture it. He and Sally Ride will be the two operators on board to do that. But this facility was used extensively by the astronauts during the development phase to help us make sure that the hardware will meet the requirements and do the job. Here's a thermal blanket being put on, and this is a multi-layered, what we call a thermal blanket, that is used to keep the hardware at a uniform temperature, or near uniform temperature, not too hot nor too cold. It keeps the heat in, and it prevents the cold, harsh environment of space from cooling the critical electrical components below temperatures that might make them fail. And that's why you see a fair bit of the orbiter, when you see some footage of it, is covered in this white thermal blanket material. There's the end effector. There's the TV camera on top of it, and on top of the TV camera, is a light. There you can see it again. The light is the black box, and the gold-colored box is the TV camera, the end effector below it.
It's a very, as you say, it's 900 pounds. It's very light. How in the world can it move something in space 65,000, how in the world? But it's 65,000 pounds. Must be a lot of physics involved.
Well, again, in zero gravity, you are weightless, but you still have inertia. And the driver there was, in the design, was to be able to exert a 12-pound force on the payload. And that's sufficient amount of force to bring the payload to rest. And we had a 32,000-pound payload was our standard, to bring 32,000-pound payload moving at 0.2 feet per second, bring it to rest in a distance of 2 feet. And so that determines how much torque one has to apply. Those were 3 astronauts. Dick Truly was there, and Sally Ride, and Judy Resnick during some of the acceptance testing of the arm.
We have a few slides which show a bit of the testing at SPAR. It was laid out on an air table, wasn't it?
We call it an air-bearing floor. Well, that's a cartoon of
overall view of the arm, which is situated right on the port side of the.
Situated on the port side, or the left side of the vehicle in the cargo bay. Here's a slide of the flight arm undergoing tests on the air-bearing floor, and you can see the mechanism underneath. That was built by a company called DSMA Atcon here in Toronto as well, and you can see pads underneath where air is being blown out to provide as a near zero friction rubbing over the top of that floor as was possible. And of course, that's just ground support test equipment that certainly didn't fly. Here you can see a technician holding a grapple fixture, which all payloads must have if we're going to go and use the arm to grapple it and do any maneuvering with it. This is a slide of the simulator facility. You can see the operator with his left hand up on the translational hand controller, as we call it, and his right hand is down to the lower part of his body, and he's operating a rotational hand controller. Here's a cartoon of the aft cockpit, where the RMS controller being on the right-hand side and the orbiter controller on the left-hand side. And here's another pictorial representation of the arm maneuvering some payload.
And the space telescope, I think.
Is that the space telescope? Fine.
And of course,
there's the actual.
The actual. I guess you really didn't know how it would look or how it would work until you got up into space and actually moved it around, because you could only move it in 2 dimensions on the floor.
Yes, well, it certainly is not strong enough to pick itself up in the 1G field of Earth. It is not designed to do that. So we were very anxious or very interested in seeing how it would perform in the zero-gravity environment of space, how smooth it was and how well or how easy it was to control. We tried very hard to make the simulators as representative of the real hardware characteristics as possible, but ultimately there's nothing like seeing it work in the environment for which it was designed.
Well, as RMS project manager, what was your main responsibility?
Well, my main responsibility was to ensure that the terms of the Memorandum of Understanding that we signed with the Americans, that all our responsibilities, our mutual responsibilities, are met. And to that end, we had to go forward and put Spire Aerospace under contract to do the design and build of the hardware and test. We worked very closely with them. We worked very closely with NASA. In fact, we worked as a team of really three agencies trying to get this never-built-before design onto paper and then ultimately turn it into hardware and push it through the very stringent test sequence which we had planned for.
Well, it seems that everything worked all right. The arm has been tested twice. What are the results?
Well, we flew for the first time on the second Space Shuttle mission, STS-2, and during that mission we had not planned to pick up a payload. We wanted to move out slowly. When you buy a new Cadillac, you don't immediately go out and drive it 120 miles an hour. You take it gently around the block at 15 miles an hour.
Mm-hmm.
And that's exactly what we did with the arm. We wanted to see if we could uncradle it and then maneuver it through all its modes. It operates in 5 different modes. So we wanted to check all those out. We wanted to see how smooth it was, how it behaved when you were firing some of the reaction control system jets, some of the big jets on the back, and the maneuvering system which are located on jets that are located out the nose, and to see if the arm, when those jets fired, would cause some vibration in it.
I mean, as it turned this way, what is the arm going to do? Is it
Yes.
going to move back and
Well, I mean, that's a very good representation.
Right.
The arm it does not have infinite stiffness, therefore it will have a certain amount of vibration attached to every time you use or apply a force which will cause the vehicle to move. So we did that, and
well, we have a tape of the 2 missions. Maybe we could talk about that. First, I'd like to say that we're going to invite you to give us a call at 752-8911 tonight, and if you have any questions for Dr. Hunter on the ARM, especially of the shuttle, or any of the results, or Canadians in space, Canadian space industry, we'll be glad to offer you to phone him up. I'm sure he'll be glad to answer any questions you might have. So the number 752-8911, and let's take a look at the tape of the 2 flights of the Canadarm, or the RMS remote manipulator system. The first one was launched in November 1981. Really a spectacular launch. And one thing I wanted to ask you, Dr. Hunter, about when it's up in space, there aren't that many forces on it, but it must be incredible to design something that's going to be able to survive a launch and a landing, and especially for this first launch of the arm, because didn't the first mission, the orbiter experienced a lot of forces which were going to threaten the arm?
Yes, we called that it was termed the overpressure. It's when those big solid strap-ons first ignite, they cause a lot of hot gases and a shock wave that is generated down onto the launch pad, and that bounces off and goes right up the whole structure, causing the whole structure to flex a bit. And this caused some very severe loads in certain parts of the structure, and if nothing had been done, we would have possibly experienced a failure in the arm. But NASA recognized that this was a major problem that had to be fixed at source. So they went and made modifications to the launch pad between the first and the second mission, and this caused the amount of overpressure to be significantly reduced to the point where we don't feel we have a structural problem anymore. And in fact, measurements from the second launch certainly showed that was true. Here you can see the solids burning from, I guess that must be STS-2 launch. And those fellows produce something like 3.5 million pounds of thrust each.
It's really quite a bit of power. And they only burn for just over 2 minutes, and they fall off. And that's something that's remarkable about the shuttle. Those rockets, they burn up, they use up all their fuel, fall off, and then they're recovered after they land in the ocean.
And they're reused. Well, there they are, jettisoning. See, they're still burning. There's jets out in the front. And Joe Ingle told me that, boy, when those jets go off, they put flame and smoke right over the cockpit. And he says, boy, you really hope that's the way they're supposed to work.
This is another view that from that mission when the external tank falls off. This isn't recoverable. This burns up halfway around the world.
Well, it's purposely jettisoned. It doesn't quite fall off, but but it's here. Yes, here it is separating, and this is footage from the STS-2 because they had a problem with the tumble valve operating the way it should. But
quite blackened.
But you can see a fair amount of charred material on there, some of it due to aerodynamic heating and other parts of it due to the flame from the solid rocket booster. Well, here we are with the looking out the, pardon me, this is from a camera within the cargo bay, looking at the STS-2 payloads that were on board, and that's a synthetic aperture radar, and the arm is over there on the left-hand side. I think something's wrong with the film.
I think it might be flipped, but you certainly get the idea. With the Earth above, even though it's below, I guess they were upside down.
Well, upside down has no meaning in space. The cargo bay doors were pointing at the Earth the entire time. That's not a bad attitude in a thermal sense. Now, here's Dick Truly operating the RMS, and you can see him maneuvering it there, and there's the system with the Earth in the background. That's quite a nice picture.
That might be a view from maybe the wrist or elbow camera. They weren't able to do all the testing they wanted to on the first flight of the arm, though.
No, there was a problem on STS-2 whereby the fuel cells had some difficulty, and they had to curtail the nominal 7-day mission down to 54 hours and return. But we did get all the primary test objectives done that we wanted to with the arm, and we picked the rest of them up on STS-3 on the mission that followed. Here's some actual footage from within the crew compartment as Dick there is maneuvering the arm, cradling it there. There was some spectacular footage that was taken both from television cameras and cameras from within the crew compartment where they looked out. They took an excellent number of stills, which I've had an opportunity to see some of them, but they took many photographs and a lot of videotape. Here's the arm. I think it's getting in a position to be stowed. And you can see the effects of zero gravity there as Dick's checklist is floating around. Here's some footage of the arm being stowed in one of the backup modes, and it's sort of a bang-bang mode. It's either full accelerator or full brakes on, and it's not a primary mode of operation. It's much smoother than that. But we had to test out all the backup modes to prove that they do work if we ever had to use them. And that was the purpose of this test. Here you can see, I believe that's the wrist that was going into its final cradle.
Well, the third mission was just, I guess, a few months ago, and you and I were both at the launch, and what did you think of it?
Well, by the time they got to T-minus 31 seconds, I thought they were serious about it, and it was a spectacular launch.
Unreal.
It was the second one that I'd seen, and I'd recommend it to anyone to go down. The films are spectacular, but to see it in real and to You feel the shock waves hitting you as it accelerates.
And it's fast. Boy, once it goes through those clouds, it really moves. So this is gorgeous footage of them opening the payload bay doors.
And
Once in orbit.
you can see the Earth in the background, and that's spectacular as well. The colors and all the clouds. It's really quite nice. Now, during this mission was the first time that we were going to pick up a payload. Here's a view from the elbow cameras. The crew are, well, here's some obvious footage where they're playing with their insects on board.
Oh yes, they had quite a few things to do other than working the arm.
But here's the arm now with the plasma diagnostic package attached. And look at the Earth in the background. That's just spectacular.
These are some funny particles that I guess they saw. The plasma diagnostics package, that was the first time the shuttle had ever been loaded. Oh, there's bald Gordy Fullerton throwing away a hairbrush. But that was an experiment that they used. Well, here you can see it picking up what we'll call the PDP, or the plasma diagnostics package. And it was a physics or astrophysics experiment.
Well, it was an experiment. There were several experiments, in fact, on that package, and it was controlled by the University of Iowa. And they indeed were absolutely pleased with all the data that they got. They were looking at the interaction of the Earth's magnetic field with the magnetic field generated around the orbiter. Here's the arm picking up that plasma diagnostic package, and we did 13, 14 hours of maneuvers with that package on board.
Were you in Houston at this time?
Yes, I was.
What would you be asked? What would you be there for? Just for consultation?
Yes, there was a total of 6 Canadians, 3 from Spire Aerospace and 3 from the National Research Council that were there. We took an active part in the mission and to assist in any troubleshooting or any workarounds that might be necessary due to either failures or problems with the arm, or problems that might occur on the orbiter which would affect our operations, like the fuel cell problem of the earlier mission, and to make sure that we got the maximum out of the time that we did have on orbit.
So this is a view from the elbow camera. I think it's a spectacular pan of the entire shuttle.
Yes, on the third mission we had a color camera on the elbow, and I would suspect that from here on in that there will be a color camera on the elbow. They'll probably maintain black and white on the wrist camera.
Well, the wrist camera didn't work on this mission. Do they know why that's not a Canadian product, by the way? That's an American camera.
Yeah, well, I believe they've managed to isolate it and have made an appropriate design change in all the cameras that are going to be used on future missions, such that the 2 cameras that failed during the last mission, that phenomena will not repeat itself.
Are these movements, are these all commanded by the astronaut, or are these programmed in?
Well, as I indicated earlier, there are 5 modes of operating the arm, and I believe these ones we're looking at now, these maneuvers, are in the automatic mode, whereby it's a hands-off operation, and all the crew has to do is to watch the numbers and watch where everything is going to make sure it's following the profile. In fact, they built up so much confidence in it, they felt that they really didn't have to concentrate that hard because the software was doing exactly as it was supposed to. But there it's being operated as a true robot. It's had pre-programmed commands, and it's off doing its robotics thing, exactly what it's supposed to do.
Well, they certainly had a lot of praise for it, and I guess from the simulations, they come back and said, geez, that's just like the simulation, or there's a few changes here and there?
Oh, the crew of both the second mission and the third mission were extremely complimentary in saying how smooth it worked, and saying things like all their surprises that they had operating the arm were all pleasant, and they had nothing but very good things to say about their experience in operating the system.
Well, we're certainly ready to entertain any phone calls you might have. Give us a call at 752-8911, and as we look at this film, maybe we'll get a few people calling in with a few questions about the arm. How many people would you say in total worked on the whole arm system?
Well, again, a project of this nature, you start off with a few people and you build up to a maximum number, and over the years, the program has gone 7 or 8 years from its inception till this point in time, and we're down to a smaller number, but we did a calculation that at one time we figured there's in excess of 650 people have participated, and the total Canadian content of the design and build is in excess of 90%. So most of the money that has been spent on the design and development of the arm has gone into labor.
Okay, I think we have a call here. Hello, thanks for phoning.
Hello?
Yes.
Yes. Could you tell me what parts of the arm are composite materials, and if any parts are composites, what design criteria did you use to choose the material?
Yes, there are carbon composites. The primary carbon composites are for the arm booms. That's for the upper and lower hollow section cores. If the camera could zoom in here, the arm booms here and here are carbon composites. The reason we selected these materials was for stiffness and for weight. Strength was not a problem to us.
How did you, the design criteria, what did you base it on? Environmental effects and so on. How did you determine that?
Well, we had a list of environmental requirements, and we were obviously looking for a very stable material that would be able to have very low outgassing and wouldn't change properties under the radiation environment, etc., and would be stable over a fairly wide temperature range. We were not interested in providing heaters down the whole length of the arm to keep it at any uniform temperature. As well, one had to worry about a long hollow cylinder, the acoustic environment, and how that might reach some form of resonance and ultimately cause structural problems. Well, we had quite a list of requirements which we laid on the contractor who built the arm booms.
Okay, thanks very much.
Yep.
Hi, thanks for phoning Astronomy Toronto.
Hello?
Hi.
Okay, I was just wondering if I could address the question of the MMU. Does the gentleman there know when the MMU will be used and what mission?
Well, it was going to be on STS-10.
Mm-hmm.
The MMU, for those who aren't familiar, it's the Manned Maneuvering Unit. It's the package,
backpack.
the package which the astronaut puts on his back, and he can then maneuver himself as a free flyer around in space. Now, that might well have been moved out to a later flight, and I'm not totally up to date as to when that is going to be, but I would suspect it's beyond December '83.
Were they going to use it for the Solar Max, retrieving the Solar Max mission?
Yes, that's a very interesting mission. If we can just talk about that a little bit, that there was a Solar Max satellite that was launched, and unfortunately there was a problem in that some wrong fuses were put in part of the payload.
Is that the one where it's tumbling and or spinning?
Yes, and so
it's like a passivization type of mission. Is that the what the MMU will be used for, or?
no. Well, what they have to do, they clearly have not met all the scientific objectives of the mission. So they're going to actually go up, rendezvous with the spacecraft, and send a crewman out with his MMU, and he will have strapped to his belly a grapple fixture, and he will then fly over the couple of 100 yards, whatever it is, over to the spacecraft, will grab the spacecraft with his hands, use his MMU to take out the rates, to stop it tumbling and stabilize it. Then he's going to strap on this grapple fixture like a dirty great belt around it, and then move around to the back side of the payload. The orbiter will then move up to the payload. The arm will reach out, rendezvous with it, grab it, put it into the cargo bay along with the EVA crewman. They will pull out the black box with the wrong fuses in and put another one in, and use the arm to take it back out and release it, and they will then carry on and complete the rest of the mission.
Had a tremendous savings because that was an expensive satellite, and they just don't have the money to build another one and shoot it up.
Well, that's true. It's a tremendous saving. It also clearly shows the capability of this space transportation system and the Canadarm to be able to go up and do an on-orbit repair, and that'll be the first one.
Can I ask one more question?
Sure, if you make it quick for us.
With respect to, as a complement to the RMS, I understand that some work's being done on free-flying teleoperators, and I was wondering what kind of work SPAR is doing in that field.
Well, I'm not sure what SPAR is doing. I'm from the National Research Council.
Sorry.
And they are probably looking at things like that, but it's perhaps not a very high priority on their scale of many things that they've got going for them.
Mm-hmm. I see. Okay, thanks very much.
Okay, thank you. Hi, thanks for phoning.
Hi, how you doing today?
Good.
Good, good. I got a quick question, actually. There's two of them. The first of them is the most simple of them, and it deals with the problem that they incurred in the first flight of the arm itself. In the press's rush to give, I guess, bad reviews to anything to do with the space program, it seemed, they did mention that there was a bit of a flaw with the Canadian arm the first time. We were wondering if you could go over exactly what it was that went wrong in perhaps more detail than one can get in the newspapers.
Certainly, I'd be pleased to. As I said, we checked out all the modes, and the last mode of operation is what we call a backup mode, which is driven by one joint at a time by the operator working a switch on our displays and controls panel. By the time we had, or at least Dick Truly had worked himself down to the shoulder, he checked out all the joints, and they worked just fine until he got to the shoulder joint. And if the camera can point down here, I'll show you on the model. The shoulder yaw joint, that's the joint that allows the arm to move back and forth in this motion. It would not drive in either the positive or the negative sense. This caused us some concern. We didn't quite understand why that occurred. And when we got the vehicle back after the conclusion of STS-2, we determined that there was a wire that was broken behind the displays and controls panel. Was in a Canadian supplied wire harness.
I see.
And we further investigated that and found that particular wire failed under tensile strength, or tensile force, pardon me, rather than any vibration failure, which normally would cause a sawtooth failure. We put this under the wires, the actual strands of the wires, under a scanning electron microscope, and you can see all this where it all necks down very much like pulling toffee until it finally breaks.
I see. So it was basically just a linkage error as opposed to anything to, having to do with vibrational breakdown in the transport.
Yes, but we further found out that we wondered what caused this and what can we do to prevent it. And it so happened that some of the technicians on the ground, after we had checked out the system to be 100% healthy before the mission, bearing in mind that we checked the system out 2 months before it flew, but for whatever reason the technicians had to access the panel next to ours, and they took the screws out and pulled the panel out without undoing any of the wire harnesses, and we fully suspect that was the tension that caused the wire to break.
And my second question is perhaps more generic, and it deals with the whole role of the space program. A lot of people are feeling that it's getting more and more difficult to justify, expensive, astronomical, and general space research, purely based on research.
Oops, we lost that caller.
That was a good question. Maybe you could address that.
Well, just briefly, the payback for this type of research is really very large. the reason we got involved in this was to develop not only a capability in building space robots, but in building robots that will have terrestrial applications. And studies that have been done have indicated a multi-billion-dollar market in robotics here in the Earth, and we clearly want to have a piece of that action. So rather than importing all our industrial robots from Japan or the U.S. or wherever, we were well advised, and I think it's a good plan to invest a little bit of front-end money. $100 million probably sounds like a lot of money, but
it pays in the end.
It pays in the end, yes.
Dr. Hunter, thanks very much for coming today. I think talking to you, one result of the third mission was the fact that it landed in White Sands, and the damn space shuttle's full of sand. Well, I brought you back a bit of white sand from White Sands, New Mexico, so if it takes you as long to get that sand out of the arm as it does my cameras, then you're going to be in a lot of trouble. Thanks again for coming, Dr. Hunter, from the National Research Council in Ottawa, and thank you for watching Astronomy Toronto. We'll be seeing you again next month.
Thank you very much, by the way.